Okay, so in this video we will be seeing the solution of one of the mechanics problem asked in 2019. So yeah, let's take few minutes to read the problem carefully. So you can see there is a spring and then there's a mass 2m attached to the spring, and then this is connected through a massless pulley here to another two block pulley system. So this is a two block pulley system. Okay, and then the acceleration of the three blocks are a1, a2 and a3. uh, Basically these a1, a2, a3 are with respect to an observer on the ground. The system is released from rest. Okay, so that's important. So the system is held at this point, and at in this position the spring is at its natural length. So basically x is 0 here, the extension of the spring. Release from rest, the maximum extension of the spring is x naught. Okay, which of the following options are correct? All right. No friction. So yeah, so you can see that this is a spring block system with no friction. So it will show a simple harmonic motion. So essentially this block 2m will oscillate around its equilibrium position, and this bottom block consisting of the pulley and the two blocks m and 2m will also oscillate along with the top block. In addition, the masses m and 2m will so basically this m will go up and mass 2m will go down with respect to an observer on with respect to this pulley. So let's call this pulley number 1 and 2. So with respect to pulley 2, mass m will go up and mass 2m will go down. So let me just uh, write again. So this pulley 1 and this is 2, and let me just put this in a box. Okay. Uh, so as I was saying that with respect to pulley 2, uh, the mass 2m will go down with an acceleration, let's call it a, and the mass m will go up with the same acceleration a. So, and in addition, this entire block shown in the orange box is going down with acceleration a1, because this is a1, so this entire system is going down with a1 as well. So what it means is that we can write a3 is basically sum of a1 and a. So a3 is a1 plus a. Similarly, a2, which is the absolute acceleration, is a1 going down and then a is going up. So this relation holds, and from there you can say that basically so from this equation minus a is equal to a2 minus a1, and from this equation you can say minus a is a1 minus a3. So these two are equal, a2 minus a1, a1 minus a3, yes. So you can see that this is the correct option. So now we will go ahead and solve the rest of the problem. Unfortunately, you'll find out at the end of this video that none of the options A, B, and C are correct, and that's very strange. I was expecting at least one of the options A, B, and C should be correct, but I don't know. It's really surprising. Anyways, this is a good problem, so we'll see how to solve it. Okay, so yeah, so we'll solve the rest of this problem, and you can yeah. So as we discussed, it's a simple harmonic motion, and one option is to do this problem from the first principle, but that may take more time. The other option is that the other approach is that we can replace the system shown in this orange box with the equivalent mass, and if we can do that, this problem becomes much simpler. So fortunately, it is possible to replace the entire block, like basically this pulley number 2 and the masses with the equivalent mass. So let's first work on that, and this concept can be used. It's good to remember this, and we can use this to solve other problems. So yeah, so I will consider generic case. Let's say this is mass m1 and this is mass m2, and remember these strings and these pulleys are ideal and massless. There's a string here. uh, so m1 m2, yeah, and uh, yeah, and assume m2 is larger than m1. So uh, with respect to pulley m2 is going down with acceleration a, like we discussed, and this is going up, and let's say this entire system is going down with acceleration a1, and let's show the force tension T, T here and then T here. Because this pulley is massless, then this should be 2T here. Okay, so yeah, so absolute acceleration of m2 is a1 plus a, for m1 is a1 minus a. So let's write the equation. Um, so this is, I'm trying to prove that this entire block can be replaced by equivalent mass, and that equivalent mass will prove it is equal to 4 times m1 m2 over m1 plus m2. So let's see how it works. So let's write the equation, Newton's second law, F equal to ma for both m1 and m2. So for m2 it is m2g minus t, it is equal to m2 a1 plus a. For mass m1 it is m1g minus t equals m1 a1 minus a. And then we can yeah, so basically I want to eliminate a from these two equations. So let's see. uh, okay, so if I want to do that, okay, another modification I will do is that I will assume this tension as T. So what it means is this becomes T over 2, and you'll see why I want to assume that as T. So these equations will change to T over 2, T over 2. And then let's say if we can replace it, the system, by mass m equivalent, then what it means is the equivalent system should look like m equivalent, and basically, yeah, this is the replacement. So it means this is still going down with acceleration a1 and tension is still t. So that's why I wanted to use t variable here. Okay, so the equation for this system will be m equivalent g minus t equals m equivalent a1. Okay, so yeah, basically what it means is that I have to eliminate a. So I can multiply the first equation with m1 m2g minus m1t over t equals m1 m2 a1 plus a, and then the second equation by m2, so I'll get g minus m2 t over t m2 a1 minus a, and once if I add these two equations I'll eliminate a, so we'll get 2m1 m2g minus m1 plus m2 over 2t, and you'll get 2m1 m2 a1. Okay, and then basically I'm trying to write this equation in this form, so I want to have only t terms, so I'll divide it with m1 plus m2 over 2, so it will become 4m1 m2g over m1 plus m2 minus t equals 4m1 m2 by m1 plus m2 a1. So yeah, you can see that if I define this as if I define this as equivalent mass MEQ, then you will get M equivalent A1. So yeah, so here we have proven that this entire system of a pulley and two masses can be replaced with equivalent mass for M1 M2 over M1 plus M2, and in this question the masses are M and 2M, so M2M, M plus 2M, so 8M over 3. Okay, so now this problem becomes much simpler. So what we can draw it again. So we have a spring, then we have a mass 2m, and the string goes over a pulley, and then there is just a equivalent mass MEQ, and this is your table. Okay, so we have to solve this problem essentially. Okay, let's see. All right. So let me explain you this how this oscillation works. To find the amplitude and to get better insight on the oscillation, we have to first find the equilibrium point of the system. And what is equilibrium point? So equilibrium point is the point where the net force on block 2m is 0, and on m equivalent also is 0. So you can think like that: if I take this move the blocks to the equilibrium position and gently release it, the system will not move, it will stay there. So if it has to stay there, what it means is that the tension in the string has to balance the mg for this block, and it also means that this tension has to balance the spring force, which is kx. So if you so yeah, so it just means that kx is equal to m equivalent g, and then x is, and we found m equivalent is 8m over 3, so it is 8mg over 3k. So what it means is that the equilibrium, so let me draw it again. So the equilibrium in the equilibrium position, the spring will be stretched by this amount. So a spring is stretched here by amount x. Let's call it x star, mg over 3k, and then yeah. So if I stretch the spring and then gently leave this system, it's not going to move, it will stay as is, and this is 8m over 3. So what decides the amplitude of the oscillation, or how does this system start to oscillate? So the way it works is one can pull or push the system by, let's say, amount A and leave it. So once that happens, so from this position X star, if someone either compresses or expands the spring by a length A, then the system will start to oscillate with an amplitude A. So let's see what is the amplitude of oscillation in this system. So for that we need to go back to this problem and see that the system is released from rest with the spring in the unstretched state. So if you come back, the original position was x was 0. So so uh, so this is our equilibrium position x star, and initially the spring was at a natural length, so x was 0. So it means the system was basically uh, uh, it was x star distance away from its equilibrium position. And it means that this is becomes the amplitude of the oscillation. So so what will happen is the block, this is the equilibrium position, it will move x star on the left side, and it will also move x star on the right side by the same amount. So you can see that here the spring is at a natural length, and at the maximum when it is expand the maximum expansion of the spring is essentially 2x star. Uh, and then in the question they're calling that the maximum extension as x naught. So what it means is x naught is 2x star, and we can just substitute the value, so it is 16 mg over 3k. So this is the value of x naught, and I think the choice is 4 mg over k, so that's not correct. Now the second part B says when the spring achieves an extension of x naught by 2 for the first time, the speed of the block connected to the spring, basically the 2m is this. So we can use energy of conservation. So what x naught 2 means is nothing but the equilibrium position, because we said that this is x naught, so this is x naught over 2. So they are asking the velocity of the block 2m when it is at the equilibrium position. So we can use conservation of energy, and here there is no friction. The work done by tension forces, the net work is 0, because this tension basically is doing positive work here, but here it is doing negative work. So the net work is done by the tension force is 0, and this is spring force, which is conservative force. So we can apply energy conservation. So we can do that. So conservation energy we can apply at x equal to 0 and at x equal to x naught over 2, which is the equilibrium position. Okay. So here the total energy is so there is no spring potential energy, and then when the block moves on the right side by x naught over 2, essentially we have the spring potential. So let's write the energies. So on the right side, when it's at x naught over 2, the spring get potential energy is half kx naught square, and so we can, yeah, basically we can assume the energy is 0 here. Let's say it's all relative. So so what happens is at equilibrium position, the block, the M equivalent has lost potential energy. So we can write the change in potential energy as M equivalent, which is 8 m over 3 then times g, and then the change in height. So it has moved by x naught over 2, so we can write x naught over 2, and then plus the increase in kinetic energy. So kinetic energy, so the velocity of 2m and then m equivalent is same, so we can just say 2m plus m equivalent is 8m over 3 v naught square. So we have to just solve for v naught square. Right, so let's do that. So this is 14m over 3 v naught square half equals so x naught we have found as 16 mg over 3, so x naught over 2 is 8 mg over 3k minus half kx naught square. So x so 64 by 9. So 9 and then to 32, I think. So that's 32 over 9. Yeah, so v naught I get is g times 32 over 21 m over k. Yeah, so if you see this answer is 3g, so even if you take 3 inside, it's a 9 over 5 inside the square root, which is about 2, but here I'm getting 32 over 21, so they are not equal. So this is the velocity I get at the equilibrium position, which is x naught over 2. Alright, so A was not correct, B is also not correct. Let's see what is C. At an extension of x naught over 4 of the spring, the magnitude of the acceleration of block connected to the spring is 3g over 10. So what we can do is that's also easy. So what we can do, we can so yeah, the acceleration is a1, and we can write the equation. Let me just copy this. Yeah, so let's write Newton's second law equation. So for an extension x, so for this block it is 8 mg over 3 minus tension equals 8m over 3a, and then for block 2m we have t minus kx equals 2m, actually it's a1, yeah, and then we can just add them, and we'll get 14 over 6. MA1 is 8 mg over 3 minus kx. So it means A1 is 6 over 14. So okay, let me just do it. Okay, and then they're asking the acceleration at x naught over 4. Okay, so x is x naught over 4, and we can get the value of x naught from here. So x naught over 4 will be 4 mg over 3k. 4 mg over 3k, and let's substitute. So a1 at x equal to x naught over 4. So you can see that the acceleration depends on the position of the block, so that's why it exhibits a simple harmonic motion. So 8 over 7g minus 3 over 7 k over m, 4 mg 3k. So this is 4 over 7. Is correct. 4 over 7. Yes. So yeah. So we'll get 4g over 7. So that's the value of the acceleration. Unfortunately, that is also not a correct option. So that's what I was telling, that it's very strange that all these three options are incorrect. After solving this problem, and then one finds out that none of the options are correct except the trivial option D. Anyway, so yeah, so that's how we solve this problem. I mean, as I said, from first principles also we can solve this. But I think it is good to use the fact that this entire system can be replaced with a mass equal to 4 m1 m2 over m1 plus m2. So I think it's good to remember this, and it might help solve some other problems. For example, there is another pulley, there is another mass, and here we have the same system. So if we have that, then it is easy to solve this problem by basically replacing this with this mass. So yeah, this can come handy in other situations.